So today we continue our discussion of chemical bonds. Remember that the atom is the smallest unit of matter, and it comes from the word that means indivisible. Each atom has a certain number of electron shells. The atomic number in a neutral atom is equal to the number of electrons, as it's also equal to the number of protons. Electrons vary in the amount of energy they possess, and they occur at certain energy levels, or what we call electron shells. And these shells determine how an atom behaves when it encounters or interacts with other atoms. They're placed in shells according to rules. The first shell holds up to 2. Each shell thereafter can hold up to 8. So if we look at the outermost electron shell, the electrons are represented by, in this case, blue dots, and these are Lewis dot structures that you see here. Hydrogen, as you can see, has an atomic number of 1. It contains 1 electron in its valence shell. Carbon has an atomic number of 6. So we have 2 electrons in the first shell, and then the remaining 4 electrons are in the outermost shell. The nitrogen has an atomic number of 7, so 2 electrons in the first, and then 5 in the second. And oxygen has an atomic number of 8. These are frequently used elements when bonding with something else. So the octet rule, if you remember back to the octet rule, this says that atoms tend to gain or lose or share electrons so that their valence shell has 8 electrons, which means carbon would like to gain 4 electrons. So those are represented here by these outlined electrons. Nitrogen would like to gain 3 electrons so that its outer shell is full. Oxygen would like to gain 2 electrons so that its outer shell is full. So why are these electrons so important? Well, elements have different electron configurations. These mean that they have different levels of bonding. For example, hydrogen and these items here, they want to gain electrons. These elements already have a full outer shell, and so they don't need to gain or lose electrons. It's important to remember Lewis dot structures to help you understand bonding. Symbols of atoms with dots to represent the valence shell electrons are known as Lewis dot structures. So here are some common ones. In group 1 we have hydrogen, lithium, sodium. Group 2, group 3, group 4, 5, 6, 7, and 8. Notice helium doesn't really follow, well, it follows the octet rule because it does have a full outer shell, but since it only has one energy shell, its maximum number, or its full electrons, is 2 instead of 8. Whereas neon, argon, and the other noble gases, they have 8. Chemical bonds are an attempt to fill these electron shells. Ionic bonds, covalent bonds, and metallic bonds are all ways to fill that valence shell. So take a moment, check your learning. What would this be the electron dot formula for? So we have an unknown element marked as X, this is not an element on the periodic table, with 1 valence electron. Would that be sodium, carbon, or aluminum? The next question, what would be the electron dot formula for this unknown element with 1, 2, 3, 4, 5 valence electrons? Would that be boron, nitrogen, or carbon? Moving into ionic bonds, these are bonds formed between 2 ions by the transfer of electrons. So when we have ions, we know that they can either be positive or negative depending on whether they have gained or lost electrons, and the atoms involved in ionic bonding actually either take an electron from the other element or they give their electron to the other element. Ionic compounds result when metals react with nonmetals. Metals, on the left side of the periodic table, they lose electrons to match the number of valence electrons of their nearest noble gas, whereas Positive ions are formed when the number of electrons are less than the number of protons. Group 1 metals have a +1 charge, Group 2 have a +2 charge, and Group 3 have a +3 charge. So if we look at an example in the formation of sodium, we have a sodium atom. Notice it has one valence electron, so it's going to lose that one electron, becoming a positive ion, +1. Its full shell would be 2 electrons in the first shell, 8 in the second shell, and sodium has 3 shells, so it has 1 in that last shell. And then when we look at formation of this ion, we see that when it loses that, we now have more protons than electrons, so we have a +1 charge. Same with magnesium. Magnesium has 12 protons and wants to lose 2 electrons, so it ends up with a +2 charge. Some typical ions with positive charges. In group 1, we have hydrogen, lithium, sodium, potassium. In group 2, we have magnesium, calcium, strontium, and barium. And in group 3, we have aluminum. So take a look at these 3 questions. First, the number of valence electrons in aluminum, would that be 1, 2, or 3? What would the change in electrons be to meet the octet rule for aluminum? Would it be losing 3 electrons, gaining 3 electrons, or gaining 5 electrons? And then what would the ionic charge of aluminum be once it has gained or lost? Would it be -3, -5, or +3? The number of valence electrons for aluminum would be 3. The change in electrons for the octet would be to lose those 3. And that makes the ionic charge +3. Since it's getting rid of 3 negative charges, that puts the positives in a higher amount. Here's another set of questions. Give the ionic charge for each of the following. What would have 12 protons and 10 electrons? Would that charge be 0, +2, or -2? If it had 50 protons and 46 electrons, would that be +2, +4, or -4? And if it had 15 protons and 18 electrons, would it be +3, -3, or -5? In ionic compounds, nonmetals in groups 15, 16, and 17, otherwise known as 5, 6, and 7, gain their electrons from metals. Nonmetals add electrons to achieve the octet arrangement, or that full outer shell. So nonmetal ionic charges can either be -3, -2, or -1, such as fluoride. Fluoride has 1 unpaired electron, so it wants to gain 1 electron, which makes it a -1 ionic charge. Ionic bonds occur between atoms of metals and nonmetals with very different electronegativity. The bond is formed by a transfer of electrons. This produces charged ions in all states. They are good conductors, and they have high melting points. When we say charged ions in all states, that means solid, liquid, gas. For example, sodium chloride, calcium chloride, and potassium oxide. So here's kind of an animation that shows what happens when 2 ions that attract each other get together. This is forming an ionic bond. We start out with sodium that has 1 valence electron, and that is given to chlorine, which needs 1 valence electron. And that sharing, or that transfer, holds these 2 atoms together. So you can think of ionic bonds as one big greedy thief dog, meaning the negative is going to take from the positive, and that holds these 2 things together. In ionic bonding, the electron from, in this case, sodium is transferred to chlorine. This causes a charge imbalance in each atom. The sodium becomes Na+, the chlorine becomes Cl-, which is that charged particle or ion, and that charge, just kind of like magnets, holds the 2 elements or atoms together. And here's an example of that crystalline structure. You can see it's very evenly spaced. Everything is organized exactly the same, which forms this hard, brittle, solid structure. When we talk about covalent bonds, this is a little different. Now these bonds are formed by the sharing of electrons. These are between nonmetals of similar electronegativity. They're formed by sharing electron pairs. These are stable ionizing particles, and they're not good conductors. For example, oxygen, carbon dioxide, C2H6, H2O, which would be water, and SiC, which would be silicon carbide. So here we're sharing a pair of electrons, and that forms a molecule instead of a compound. Just a note, when we start to talk about polyatomic ions and diatomic molecules, these are all bonded by covalent bonds. There are two kinds of covalent bonds, either polar or nonpolar. Nonpolar is when the electrons are shared equally, such as a hydrogen molecule or a chlorine molecule. Two atoms share one or more pairs of outer shell electrons, and if they're pulled equally toward the opposite nucleus, then it's a nonpolar covalent bond. Polar covalent bonds are when the electrons are shared unequally, such as water. This is an uneven match. One is pulled more strongly toward the nucleus of the other one. So oxygen has a slight negative charge, hydrogens have a slight positive charge. They're pulled more strongly to the oxygen. And then we have finally metallic bonds. These are found in metals. They hold metal atoms together very strongly, and it allows for certain metallic properties. The electron cloud kind of forms around all the atoms together, makes them good conductors at all states, such as solid, liquid, gas, gives them luster, which is kind of that shininess, and gives them very high melting points. For example, sodium, iron, aluminum, gold, and cobalt. Metallic bonds are kind of like the nucleus they're all sharing the same bones. There's enough to go around for everybody, and nobody's fighting. Kind of makes one giant electron cloud around these atoms. Metallic bonding also allows metals to form alloys, which means metals don't actually combine with other metals. They form alloys, which is a solution of a metal inside a metal. For example, steel, brass, bronze, and pewter. You've got metallic forces that kind of push the atoms of one apart, allowing the other type of metal to interact. So state the type of bond for each of the following. We've got NaCl, C2H6, NaCO3 taken twice, and gold. Just so you are aware, since we haven't talked about it yet, CO3 in parentheses here is a polyatomic ion. NaCl is an ionic bond. C2H6 would be a covalent bond. Notice here we have a metal and a nonmetal. Here we have two nonmetals. Here we have a metal and a polyatomic ion. So this actually gives us both ionic bonds and covalent bonds. The CO3 is a covalent bond, but when we bond that with the metal, then we get an ionic bond between the polyatomic ion and the metal. And gold is a metallic bond. So just a little more information, hopefully some visuals to help you understand these types of bonds. And if you have any questions, please let me know.